Hello everybody, my name is Diego Arcos from Universidad de las Fuerzas Armadas de Este from Ecuador. I am going to present the paper entitled Fuzzy Control-Based Energy Management System for Interconnected Residential Microgrids Using the Forecast of Power Generation and Load Demand. This is a collaboration work of Universidad de las Fuerzas Armadas ESPE, Universidad Politécnica de Cataluña, Catholic University of Leuven, and Energy Bill. I want to thank the Flemish Inter-University Council and the Belgium Development Cooperation for supporting the project Mira Este, which is developed between Universidad de las Fuerzas Armadas ESPE and KU Leuven. This is the outline of this presentation. First, I am going to present a brief introduction of the topic under study. Next, I will describe the residential microgrid under analysis. Then I will talk about the operation of a single grid-connected microgrid. After that, I will present the interconnected microgrid scheme and the fuzzy logic control design to perform the power exchange between microgrids. Then I will show some simulation results, and finally, I present the conclusion of this study. Nowadays, human growth and development have a directly proportional relationship with energy consumption. For this reason, and to promote the use of renewable energy, the use of residential photovoltaic systems such as rooftop PV systems have increased in many countries. However, due to the variability of power consumption and solar resource, these photovoltaic systems feed energy to the grid in a variable way, which is of great concern to the grid operators. Therefore, it is necessary to minimize fluctuations and power peaks in the power profile exchanged with mains. Thus, this study proposed an energy management system to control the power exchange between two residential microgrids. This study aims to use one microgrid's extra power to charge the energy storage systems of the other microgrid to minimize the energy injected to the mains of one microgrid and the power absorbed from the mains to the other one. This study considers two residential grid-connected microgrids. Each microgrid comprises a photovoltaic generator of 6 kilowatts, an energy storage system that includes a lead-acid battery bank with a rated capacity of 72 kilowatt-hours and a load of 7 kilowatts. In this figure, the direction of the arrows implies a positive power flow, so the generation and load profiles are always positive, whereas the battery power is positive for battery discharging and negative for battery charging. Similarly, the grid power is positive for power injection from the mains and negative for power injection from the microgrid. Since we are considering two neighboring microgrids, we have assumed that both residents receive similar amount of solar radiation and have different load consumption. For each microgrid, we can define the grid power as the difference between the load consumption and the generation power provided by the photovoltaic generator and the energy storage system. Similarly, we can define the microgrid net power as the difference between load consumption and generation powers. Each microgrid operates with its own energy management system based on a fuzzy logic control and microgrid power forecasting. This energy management system defines the grid power profile as the sum of three components. The first component is used to provide an average power profile by means of a central moving average filter that uses the samples of the previous 12 hours of the microgrid net power and the samples of the next 12 hours of its forecast. The second component is used to keep the battery state of charge close to the 75% of the battery charge based on the current battery state of charge and the average battery state of charge of the previous 24 hours. And the third component is provided by the output of a fuzzy logic control block based on the battery state of charge and the forecast error of the previous 3 hours, and it is used to reduce power fluctuations and power peaks in the grid power profile. On the other hand, the battery power is defined as the difference between the microgrid net power and the grid power profile. Now we can see the interconnected microgrid scheme. Here we have modified the block diagram of the energy management system based on power forecasting, and we have included the power exchange block. This block modifies the battery power so that a certain amount of the battery is transferred from the microgrid with surplus energy to the microgrid with an energy deficit. Therefore, the battery power is redefined by adding the power coming from the other microgrid and subtracting the power given to the other microgrid. This power exchange is performed by another fuzzy logic control block of 3 inputs and 2 outputs. On the one hand, the inputs are the difference of prediction error, the difference of power availability, and the difference of battery state of charge of each microgrid. On the other hand, the outputs are the powers exchanged for each microgrid. Here we can see the membership function for input variables. We have defined 4 membership functions, 2 triangular and 2 trapezoidal, for the difference of prediction error and the difference of power availability. In contrast, we have defined 2 trapezoidal membership functions for the difference of battery state of charge. Here also we can see the variation range of each variable. Also we can see the membership functions for the output variables as well as the fuzzy logic rule base in charge of performing the power exchange. Here we can see that the power exchange occurs in only one direction at each sample period, either from microgrid 1 to microgrid 2 or vice versa, but never simultaneously. Now I want to present some simulation results. These figures show the grid power profile and the battery state of charge of each microgrid achieved before and after the power exchange. We can see that fluctuations and power peaks have been reduced after the power exchange between microgrids. Also, we can see that the battery state of charge of each microgrid is still keeping between secure limits. Here you can see the resulting values of the quality criteria of the grid power of each microgrid. The reduction of all quality criteria is notorious, especially on the maximum power run rate. In addition, these figures present the battery state of charge of both microgrids for a 9-day period, where we can see that both batteries are almost synchronized after the power exchange. These results show that the power exchange between microgrids allows increasing the efficiency of each microgrid compared to its operation individually. Now the conclusion of this work. I have presented a fuzzy-based power exchange management between 2 grid-connected interconnected residential microgrid with renewable generation and battery storage system. The energy management system uses generation and demand forecast to perform the power exchange between microgrids. Power fluctuation, which means the power fed into the grid and the power injected by the grid, have been reduced by 50 and 60% in microgrid 1 and microgrid 2 respectively. The battery state of charge evolution has kept close to the 75% of the battery rated capacity, and the operation of the microgrids under this scheme has led to the battery state of charge of both microgrids being synchronized, which allows improving the behavior of the battery state of charge of each microgrid by working together rather than individually. Thank you very much for your attention. If you have any questions, do not hesitate to contact me.